Okay, so the next thing we're going to talk about is determining a three-dimensional geometry or structure of molecules, of course based on our knowledge of Lewis structures and how to build molecules. Now it turns out that figuring out the shape, or the overall shape, three-dimensional structure of molecules is very simple, because all we have to think about is what is going to cause a different shape. And it turns out it all has to do with the repulsions between electron groups. So here we have a molecule with 4 atoms, a central atom bonded to 3 additional atoms. Okay, these electrons in these bonds, and which we'll start to refer as electron groups. So electrons in a bond, a single, double, or triple bond, or electrons as lone pairs, we'll refer to as electron groups. And we know that these electrons are the same charge, negatively charged, and they will repel each other. The distance that they can get apart, the furthest distance that they can get apart, they will, and this will determine the overall three-dimensional structure. This is more correctly known as valence shell electron repulsion theory to develop overall structure of molecules. So in trying to figure out the three-dimensional structure, what we're going to need to do is figure out how many electron groups a molecule has, or how many electron groups are around a central atom, and then figure out how far those electron groups can get away from each other in three-dimensional space. So the first example would be a linear geometry, and this sets up when the central atom has 2 electron groups. Okay, how far can these 2 electron groups get away from it? 180 degrees. It turns out that if you have a linear structure and this atom starts to move this way down, it of course will get further in this direction. That angle will get greater than 180 degrees, but this angle will get less than 180 degrees, and so there will be some repulsion to push it back. So the overall geometry will be a linear structure, whereas the 2 terminal atoms bonded to the central atom will be 180 degrees apart, linear in geometry. Okay, so that's for 2 electron groups. If we go up to 3 electron groups, what we have is a trigonal planar geometry. And in this region, the atoms, or the electron groups, can get 120 degrees apart from each other in 3 dimensions. Okay? One of the very important points about a trigonal planar, as opposed to a trigonal pyramidal, which we'll speak of soon, is that all 4 atoms are on the same plane. If we put this molecule, this BF3 molecule, on a table, all of the atoms would touch the table. They're in the same plane, 120 degrees apart from each other. Okay. The next geometry will be one with 4 electron groups, and what shape they take on is what's known as a tetrahedron in geometry, sort of pyramid-shaped structure. And what happens is each of these atoms, pictured here is sort of tying 4 electron groups, 4 balloons together to represent the electron groups. These can get 109.5 degrees from each other in three dimensions. Okay, an example of that would be methane. Methane is a 4 electron group molecule. Each of the bonds between a carbon and hydrogen represent the electron groups, and they can get 109.5 degrees away from each other. Very important here is that no longer are all the atoms in the same plane. Okay, we saw that the linear geometry and trigonal planar geometry, all of those molecules are in the same plane. It turns out, depending on how you look at this, you can talk about several planes here. The 3 bottom hydrogens, if we set this molecule on a table, these 3 hydrogens would be touching the table. The carbon atom would be in a second plane, slightly raised from that, and then the 4th hydrogen atom would be in a 3rd plane. Okay? One of the things we might want to be able to do is draw this structure, this 3-dimensional structure in 2 dimensions. And instead of drawing a ball and stick geometry, which some of us probably can do, some of us can't, what we're going to do is wedge and dashes to do so. Okay, by showing a methane atom like this, we can show the different planes that the atoms are in. Okay, so what we're trying to show you is that this hydrogen, this carbon, and this hydrogen are all in the same plane, corresponding to those atoms. This hydrogen is coming out at you, facing you, coming out of the plane of the board, as they say. And of course, this hydrogen with the dash mark is going away from you in the back of the board, away from the plane. Okay, and so that's another way we can show three-dimensional structures in 2 dimensions on paper. Okay, so that again is 4 electron groups, tetrahedral geometry. If we go to 5 electron groups for an expanded octet, for such as PCl5, we can see that there are 2 regions where the chlorine atoms will take either equatorial positions, sort of think about in the center on the equator, and then of course axial positions. Now depending on where the atoms are, they can either be 120 degrees away from each other or 90 degrees away from each other. And again, we have several different planes we can discuss about. The equatorial chlorines are in the same plane. If we're going top to bottom, here's a plane, here's a plane, here's a plane. Or we can also think about these 4 atoms in the same plane, and then this one coming out behind you, and this one coming out towards you. Okay, but again, how far away can these electrons get from each other? The basis of VSEPR theory, valence shell electron repulsion theory, and that of course is 90 degrees axial, 120 equatorial. Now, if you throw in another electron group and go to 6 electron groups, you have an octahedral geometry. Okay, and so instead of the equatorial electron group being 120 degrees from each other, now your equatorial and your axial angles are all 90 degrees.